Good evening, everybody. This is the Group 9, and we are going to present you our finally project delivery from Herramientas Computacionales 1.
The purpose of this study is design, create, and simulate a centrifugal pump to analyze and compare the manufacturer's database simulation values. The pump is one of the most used machines in the world, and there are three principal functions that the pump needs to have. Transport liquid fluids to different positions, change pressure level between two different precision points, and compensate the energy losses of different aspects in the system. CFD simulation has been used to analyze flow in centrifugal pumps and has enabled a more detailed understanding of flow phenomena in these machines. Some of the current research topics in CFD on centrifugal pumps include centrifugal pump transient flow simulations, analysis of fluid dynamics and cavitation, optimized impeller design, and non-Newton flow simulations. There have been significant advances in CFD simulation for viscous flow pumping. Pumps for viscous flow are typically designed with larger diameters and lower rotational speeds. Viscous flow pumping can increase the cavitation. A proper NPSH consideration must be made to prevent this. Some studies with CFDs have been providing insights into cavitation behavior, and there are some considerations. A proper boundary conditions are crucial for accurate simulation of cavitation in pumps. In regions where cavitation is likely to occur, a finer mesh is necessary to capture the small-scale phenomena.
This is the procedure we got during the project. It begins with the use of Excel and Autodesk Inventor with the impeller and shell design and its assembly after. And then we get into Star CCM Plus, which we use to create the mesh and the selection of physical models that we can use, changing the range of the flows in different fluids, in this case water and oil.
In order to do the impeller and shell design, the operation curve provided by the manufacturer of the pump was used. We utilized the optimal flow rate and the optimal head provided by the operation curve in order to design the parameters and dimensions of the pump shown in the table. We can also see a rough sketch of what the pump would look like. After this, we proceeded to do the pump in the CAD model.
In this slide, you can see some important measures for the CAD design.
For the mesh generation, an automatic polyhedral mesh was used, with the following parameters shown in the table. The goal was to have a y plus value of less than 5. We saw that increasing the number of prism layers and the prism layer's total thickness helped achieve this goal.
After the mesh generation, we had to do the mesh independency, which consisted in choosing 3 different base sizes and developing the mesh itself. You can see above the results, and in this case we chose the mesh that was 1.3 times B2 because the cells were between the range specified in the project. But we did have a problem, which was the Y plus, because it was quite bigger than expected. The maximum value was supposed to be 5, but we did have some problems right there, and we think this is because of the blades, because the blades apport a lot of momentum and a lot of Y plus, and you can see this in the results in the Y plus graphs. Here you can see the table that I showed you before in a more graphic way. As I said, we chose the base size of 1.3 times B2.
In physical models, we have to know the importance of Reynolds number in the different fluids. In this case, with water and oil, we have to estimate with this number that are turbulent fluids. For that reason, we have to use the K epsilon model for that. Furthermore, we use other models like segregated flow and constant density for that. In the initial boundaries conditions, we are evaluated 5 flows, including the manufacturer BEP and the initial calculating BP. The principal results that we can see in pump performance is like in these two simulations, like in water and in oil, we can see a clearly difference between these two fluids. It happens because many factors like the density and the viscosity. In our principal results, we compare the difference between the simulations and the total heat by the manufacturer and the efficiency between the manufacturer and the other two simulations. The last result comparing the performance between the manufacturer and the CFD, we know the data obtaining are in the correct range. So in consequence, we know that the condition don't affect the simulation and can operate in the right form.
Analyzing the velocity profile in the pump, it can be observed that for each flow rate used and for each fluid, the behavior is similar, with low magnitudes at the inlet and outlet and higher magnitudes in the zones near the blades, especially the T's. The reason of this is because it corresponds to the rotation region, where the fluid will be pushed by the blades, causing it to acquire higher velocity. These are the velocity profiles for water and mineral oil, both at a flow rate value of 125 cubic meters per hour. These are the velocity profiles for water and mineral oil, both at a flow rate value of 250 cubic meters per hour. These are the velocity profiles for water at a flow rate value of 270 cubic meters per hour and mineral oil at 272 cubic meters per hour. These are the velocity profiles for water and mineral oil both at a flow rate value of 310 cubic meters per hour. Analyzing the pressure profile, it is observed that for each simulated flow rate, the pressure in the water fluid is higher than the pressure in the oil fluid. This is mainly due to the difference in densities of the fluids, as a higher density leads to greater mass of the fluid, resulting in the increment of the hydrostatic pressure.
Here we can see the Y plus values for the impeller in the simulations of water and oil. We can see that in most of the impeller, the Y plus value has a value of less than 5. However, there were some complications, and in the corners of the blades, a Y plus value of very large scale was generated. We now see the Y plus value in the rest of the simulations. We see that, again, the Y plus value in the majority of the impeller is very low and less than 5. However, once again, in the blade corners, we can see that a Y plus value of very large scale is generated, meaning that the simulation cannot produce a very accurate velocity prediction in these areas. Now we proceed to see the absolute total pressure scenes that will help us analyze the cavitation produced in the pump. We found out that we needed a pressure higher than 2.3 kilopascals in order to not have any cavitation in the pump. We can see that in the exteriors of the impeller, this pressure is achieved. However, in the center, we have a pressure that is lower than the saturation pressure for the liquid. In this case, we could have some cavitation produced in the center of the impeller when the liquid first goes into the pump. However, we can see that as the flow rate increases, the pressure in the center of the impeller also increases, meaning that at a higher flow rate, less cavitation will be produced. When reaching the free delivery flow rate, we can see that the pressure in the center of the impeller can rise above the saturated pressure point of the liquid. Now we will proceed to see the vector velocity animations for each flow rate of the simulations. We can see that as the flow rate increases, the fluid can flow more uniformly and it flows closer to the walls.
In conclusion, the geometry and simulation parameters defined, such as dimension of the system, the type of mesh, initial conditions, and the physical model were correctly assumed due to the FC value, the total head value, and the brake power are close to the real values. However, it must be taken into account that CFD pump operation efficiency is higher than the real one, since it is not taking into account the infinite friction losses, volute friction losses, these friction losses, and recirculation losses.